we've looked at is, we're looking at time response of second order systems. This is one way of representing a second order system. All right. Here, the second order comes from order of denominator is 2. This is a second order polynomial, right? Okay. So this is a second order polynomial, or this is a, what else can you call this denominator? It's second order. Second order polynomials are also called
quadratic equation.
Quadratic equation. Okay. So if you look at a quadratic equation, the roots can be, these are the 4 options, right? They cannot be anything else. The roots of a quadratic equation are either real and distinct, real and repeated, complex, or imaginary. So if the roots are real and distinct, that makes the system a overdamped system. We call that a overdamped system. We saw this last time. If the roots are real and repeated, that's a critically damped system. If the roots are complex, that's a underdamped system. And if the roots are imaginary, that's a undamped system. Okay? Undamped or a marginally stable system. Now, this is another way of, or a more natural way of representing a second order system. Here, it is represented, this representation is in terms of the natural frequency and damping coefficient. All right. If you look at, we need to correlate this damping coefficient with what kind of systems these are. So as Anthony said, undamped, it just the English meaning of this would indicate that zeta is probably 0. The damping coefficient is 0, right? What is underdamped? Any?
0 from 0 to 1.
Right. So it is 0 less than zeta less than 1. How about here?
1.
This is
anything greater than 1.
Greater than 1. Okay. And this explains, what do you understand by damping? So here, what example did we think about for an undamped system?
A system that's undamped.
Not example. You remember from last time?
Kitchen door. A broken door or something.
Kitchen door that swings freely.
But that will have damping, right? Those balls we talked about.
Oh, the pendulum thing.
Yeah, the pendulum thing.
So,
they will just
so
do
the
that. Newton's law will apply anywhere.
No, I'm talking. Never mind. So those.
They'll keep on, right? There is no damping. In that, damping essentially means
it'll slow it down to
something slowing down.
Eventually come to a stop.
Okay, it will some resisting force. So if there is no damping, even for a satellite, for aerospace engineers, you should always think about satellites in high Earth orbits. For example, the moon is a satellite, right? It's a natural satellite. It's been orbiting for millions of years.
Forever.
And it's been doing that because there is no damping. If there was damping, it would come down. And that's what happens with many satellites which you put really deep in space. Not really deep, but even medium Earth orbits or geo orbits, right? They will just do that unless there is no atmosphere, there is no damping. Okay. Underdamped example, if you look at the kitchen door or some kind of door with a damper, how will the underdamped system close? Or in terms of aircraft, if it is supposed to reach a particular altitude, what will it do?
It will oscillate first and
right. It is underdamped, so it will do that and then gradually
eventually hit
yeah.
1.
So underdamped are, as the word suggests, so this is critical. Under. It is not sufficiently damped. You can say that. Okay, so it will go above and then slowly. So that is the reason when you see the zeta coefficient is 0 to 1. Critically damped is, it is just enough. Okay, it won't go under and it will just do that. Okay, so critically is the key word here, and this is a very difficult system to achieve per se.
That's what we want, correct?
It would be a very ideal system. Okay. Overdamped. The next is overdamped. Overdamped is.
So Dr. Sunday, it's real and repeated, not real and separated.
Say it again.
For number 2, you say it's real and repeated.
Right.
So it's not separated.
This is separated as this.
Okay.
Real and distinct. It means separated. Okay. So here, real and repeated means the roots are the same. Got it? So here it is critically damped, and it is very difficult to get repeated roots for an actual system. Okay. Overdamped is, this is a more robust system. Okay. If you look at any nuclear process, since some of you are in the Navy, right? Most systems you design there are overdamped systems. You want robust systems. You cannot design an underdamped system if you are in Navy. Let's say it's involving some kind of nuclear fuel or nuclear process. You have to design it as overdamped. You have to be overly cautious because it should not go out of control. All right. Now, we'll look at performance parameters, and we'll look at it in the context of underdamped system. So underdamped systems, these are, you can say, the most common. Okay. So if you look at an underdamped system, you look at the step response, or specifically unit step response. So this is the T, this is the C of T. And this is my reference. Since it's unit step response, this will be 1. Okay. If you do a plot of unit step response for an underdamped system, it will look something like this. So here, we'll look at performance parameters. Can you tell me performance parameters, anybody? Again, I think we saw this for the first order system. It is very similar, except that there is no time constant, okay, and there are two other parameters introduced. There is there is peak time and there is percentage overshoot. These were not there in the first order systems. Okay. So here, what is this? Anybody? This point is essentially C max, the max output or the max response. Okay. And I'm going to use the written here. This is peak time. This is rise time. This is settling time. This is overshoot. All these parameters are kind of self-explanatory. You can go look at the definition as well. Okay. So rise time, it's essentially defined as the time taken for the system to go from 0.1 of the final value. The final value here is 1, okay? Because you see where it is settling. It is settling around 1, right? 0.1 of the final value to about 0.9. So you can say this point is 0.1 of C of t. This point is 0.9. So rise time is essentially the time taken for the system to go from 0.1 of the final value to 0.9. All right. It's like you have, again, recall this 0 to 60 or 0 to you have this rating for vehicles, right? 0 to 60 in so many seconds. That is the rise time. Okay, the rise time will essentially tell you how what is the slope, what is this, how steep is the climb. Okay, so if the amount of time taken is less and less, what happens to the slope? It becomes steeper and steeper. You understand? For overdamped, it is this. It looks like this. Okay. For critically damped, it is like this. For overdamped, it is like this. All right. So it is from here to here. You see, this is how it follows. The slope tends to become steeper and steeper. Okay. You have very basic formulas you need to use. I'm going to give you those formulas directly. You can derive these as well. Tp is equal to pi over omega n root of 1 minus theta square. Okay. T percentage overshoot is e to the power of minus zeta pi divided by root of 1 minus zeta square. Okay. This whole thing multiplied by 100. Ts is 4 over zeta omega n, and Tr we'll refer figure 4.16 in the textbook. Any questions on these? Do you understand conceptually what these mean? You're okay? Julian? Boris?
Did you?
I'll do an example and show you, but do you understand? Do you understand this and this?
I missed what you said that symbol was. I missed what you said that symbol was. That signal or epsilon?
This one?
No,
Which one?
You got like
This one?
Yeah. That.
Zeta.
Zeta?
Yeah.
Okay.
Zeta. Zeta. Okay. So I'm going to erase this part. Okay. an example. I'm going to say find omega n zeta TP percentage overshoot TS ER for G of S is equal to hundred over S square plus 15S plus 100. Okay. So your solution to this would be, this is the simplest of problems. Recall G of S is also equal to omega n square divided by S square plus 2 zeta omega ns plus omega n square, right? So if I say this is A and this is B, comparing A and B, what is omega n? Anybody?
Like the value?
Hmm.
Be 10.
Right. So you have to always compare the denominators, okay? And I'll tell you why. It's 10. It is plus or minus 10, but natural frequency is not negative. Okay? Natural frequency is always positive. There is no meaning for natural frequency being negative. Can time be negative? So frequency cannot be negative. Is there, what does negative frequency mean? Sorry?
I mean, it's 1/2 seconds, so you can kind of have negative time.
You can?
Yeah, essentially. You would travel back in time and get negative time.
Alright. Okay.
But let's pass this class, I guess.
Huh?
Cover that next chapter.
I get let's pass this class.
Zeta, what is zeta? Anybody?
7.5.
5. Wait, no, 7.5.
7.5?
No, it's not. Because, WN is 10. So it's going to be a fraction.
It's going to be a fraction, yes.
I don't know
It's
what
going
the
to be
fraction is.
3/4. 3/4. Because,
20 times 0.75 is 15.
wait, hang on, no, I did that wrong.
Yeah, that's right.
Did you get 3/4?
It should be.
15 divided by 10 is 1.5. Divided by 2 is 0.75.
Is it?
Yes.
Sound right.
Do you want me to crunch that?
Hmm?
Yeah.
It's already crunched. So what kind of system is this?
It's a, underdamped.
It's the underdamped system, okay? So here you can say this is a underdamped system. Alright. Now how do you calculate TP? It is pi over 10 root of 1 minus 0.75. Okay. And the value here is 0.475 seconds. Keep in mind, if you get this as let's say greater than 1, what would be peak time?
Wait, say that again.
If you get zeta greater than 1,
Greater than 1.
Hmm.
It'd be imaginary. Well,
Was for units? I thought for unit step response we used 2.2 divided by something. So why is it?
No, what I'm saying is, if zeta is greater than 1, what system is it? Overdamped.
okay, so you're saying
So what is the
Imaginary.
peak time?
It would be just 1.
it'd be pi over 10.
I don't want an actual
Value.
answer. It is,
0.
what is percentage overshoot? What is overshoot for a overdamped system? How much is the overshoot?
0.
0, right? So what is the peak time?
It's gonna be 1.
Infinity. It's never going to peak. You understand? If you look at this zeta, you remember these. Well, we'll solve this first. So percentage overshoot, you just use that formula, okay? And you're going to get 2.838.
Notice when we was doing that 2.2 stuff, what was that for? Was that just for
That was the first order system.
first order system?
This is the second order system. Okay. And TS is point. Again, you just have to use that formula.
Yeah, we don't need math. We don't need to mathematically know how you came up with these formulas, right?
No, I won't ask that. You may want to know it, but I won't expect you to demonstrate that. Okay. And for exam, you will be allowed to have a formula sheet. You don't even have to remember the formula sheet. Okay? And finally, TR. Can you say something about TR from these values?
No, because it says refer to figure 4.6.
Think, Anthony. First.
I'm going based off of the information that you've given us. Is that supposed to be figure 4.16?
No. Can you say something about TR looking at that figure
It's from
It has something to do with 0.9 and 0.1.
in correlation to these numbers?
it's less than 0.53.
Yeah, see, that is what I'm asking. It's less, right? It has to be less, right? Because TP is greater than TR, the way it is defined. So when you do the TR, if you get more than these two numbers, either these two numbers are incorrect or TR is incorrect. You get it?
Could you not do TS over TP and find a ratio to find your TR, or do you have to use that formula?
No, it's not the ratio though. TP is the time taken from 0 to reach that peak, okay?
Okay.
TR is the 0.1, start from 0.1 of the final response to 0.9. That is the time taken. It is not, it depends on the slope. Okay, TS is once it settles down, how much time it takes to settle down. Alright. So TR here is 0.23 seconds. And it's easy to use that figure, okay?
So you just look at the figure and it gives you that?
You can look at the figure and there's a damping ratio and a rise time, normalized rise time plot. Okay, you can look at that. When you do the examples or homework assignments, you'll learn how to use it. It's fairly simple. Any questions on these? One of the things I will need you to do is, you see, this is very critical, okay? If you are given a black box, okay, and you're told that it's a second order system, right? But you don't know what is inside. You can only provide input and measure the output. That is when, without even knowing what is inside, you can just simply use this formula and model that system. This response you're getting is independent of the system you know. You can simply get this, you can apply an input and measure this output. Experimentally do that and figure out these things and then model those systems. Okay, so you'll be asked to do some similar problems in exam and in your assignment.
How are you getting that number? Were you going from the X or Y or what?
Say it again.
How are you getting 0.23 seconds?
So you have damping ratio, right? What is the damping ratio? We found out that 0.75, right?
Right.
So 0.75, you go and look at the normalized rise time. That is rise time into natural frequency.
Okay.
Right? It will be around, rise time into natural frequency is about 2.3. Okay. And so rise time to natural frequency is 2.3. Natural frequency is 10.
Okay.
So divide by 10. 0.23. Got it? Okay. Now, as I told you, all right, so let's look at another example problem.
Do it. No, this way.
Don't break the rules, man.
How long I do?
So the ladies can be paying.
I got superhuman strength, bro.
The system has a damping ratio of 0.15 and in natural frequency of 20 radians per second and a gain of of 2, find the transfer function and plot the general response, poles, etc. Okay, a question will be given to you something like this. So here, the first thing you'll do is, you know this, right? A more generic form of general second order system is written like this, okay, where k is the gain. Alright, so your transfer function will be 2 into 20 divided by s square plus 2 into 20 into 0.15 s plus 20 square. This will be 440, sorry, square, right? $800 and s square plus 3 to the 6. Plus 400. This is a system. Okay, now how will the pole plots look? First, let's look at the general response. If I ask you to draw the general response, step response, how will it look? Anybody?
Oh, you know the 0.15.
Right, so how will it look? It's what kind of system is this?
That is a underdamped.
Underdamped system, right? So your general response will look like you got it? Underdamped system. Right? Your pole plot,
You gotta figure out the roots.
to figure out. Right? So here it will be somewhere like this. It's a complex system, right? It's a the roots are going to be complex because it's a this is very, very critical. From this you can figure out the general response will look like this, the general pole plot will look like this.
Right. You just don't know the numbers.
You just don't know, you can figure out the numbers later. Okay, you can arrive at this. And then you can even calculate TP, TR, TS, percentage overshoot.
You'll need to calculate that though for the question. Right.
You need to calculate that. So you just use this to calculate all of that. Or you don't even need this. You're given those two, right? You're given zeta is 0.15 and omega is 20. You just have to substitute, use those formulas to calculate. Got it? The other problem I'll ask you is, if I give you these values,
Can we work backwards?
can you work backwards? Yeah.
No, we can't.
You lose points.
Well,
Don't pass the course.
I'm just telling you right now.
I mean, you can find your WN. If
Huh?
you gave us TP,
Right. So
but if you
here,
gave us overshoot, we might have some trouble with that.
right, if you give these, so for example, if I give you let's say this. What will this yield if I give you this?
I mean,
It'll give you
Finally,
zeta.
Zeta, right? Zeta, you put it in here, you're given this, you'll get omega n. Okay? You get zeta and omega n, you form this system.
Can't do that. Sir.
don't give us overshoot. Give us like TP and TS.
You just give us the answers.
Yeah, I'll give you even the converted formula also I'll give you. Okay? The converted formula, you don't have to convert it yourself, it is in there. I'll give you this formula, for example. You just need to use, and now don't tell me we don't know how to use the calculator. Okay. You'll be given this formula as well. Zeta is, Anthony,
Yes.
did you listen to what I said?
Yes, sir, I did. What did you say? I'm just kidding.
You can use this formula directly. Okay. I find it a little bothering that some of you cannot do this conversion.
I can do it. It's just gonna take some time.
Yeah. And
Why don't you go over it real quick?
You Taurus, you don't need to go back.
it's just taking the ln of this thing, okay? If you take the ln of this, it'll be this multiplied, or you just divide by that, and then you transfer everything here, it will be like this.
You're horrible at math.
No, I'm not.
You
Taurus.
really are.
How do you
You
know?
make miscalculations all the time. That's why.
Usually when there's like a billion
I was just working it through my head.
little
Right.
math problems and they're,
So her
they're
go first.
tedious,
I said
like
so her go
propulsion.
No, you
That
don't.
one
I-
assignment,
You
that
can do it
900
yourself.
equations
Take the
on-
ln on either side. This thing will, this e will vanish.
Where did that T1
You know
come
what I'm
from?
Huh?
talking about.
Where did that T1 come from?
Which t1?
At the bottom.
That's 5.
That's
Right.
5.
Oh, that's why I was getting confused.
Your tie's not even
Just
tied,
divide
right?
by 100.
I know. I'm at this point.
Okay.
I'm waiting till the later.
Why did your
That's on my class.
hold on, let me see.
You look terrible.
I really don't.
You smell terrible.
You got, is that a Y?
It's crooked.
0.05?
What is that? A 2 degree slant?
You have, so you have percentage overshoot divided by 100, right? Equal to e to the power of minus
20 push-ups. That actually probably make you feel better.
zeta pi divided by 1 minus zeta squared, right? So you have ln of
Pick one.
percentage overshoot
Talk to you now.
divided by 100 is equal to minus
Not in this room.
zeta pi divided by root of 1 minus zeta.
Anytime.
And if you square, you're going to get this whole thing squared, right? Ln square. Zeta square, pi square.
Mm.
Right?
Mhm.
And you can do 1 minus zeta square is equal to pi square. So zeta square, pi square divided by ln square percentage overshoot divided by 100. Okay. And you can do zeta square 1 plus pi square divided by
Where do you get 1 plus y squared? Y squared.
Hmm?
Hey, now I'm confused. Start over. Okay. Doctor said, you sure you're doing this right?
Hmm?
You sure you're doing this right?
yeah.
Why is it 1 plus pi squared?
So if you take zeta on the other side, it will be zeta square, right? plus this thing, the whole. So if you just take zeta square out, you're going to get 1 plus pi square divided by this equal to 1. Alright? Now all you need to do is zeta square is equal to 1 over
Oh, I see what you did. Never mind. Gotcha.
1 plus pi square divided by.
You take the square root of that and you get zeta.
Okay.
Wouldn't that be at the top though?
Huh?
No.
Yeah, well,
Hang on a second.
It will be zeta square is equal to ln square percentage overshoot divided by 100 ln square percentage overshoot 100 plus pi square. And if you remove it, or
how'd you get the bottom?
so this you just multiply this here, okay? Right? And you move this on the top.
When you is that one attached to that one?
It's not attached. It's separate, right? It has to be separate. So here, this zeta square will go on the other side, okay? If it goes on the other side, it will be zeta square plus zeta square pi square divided by this whole thing. So you just separate out zeta square, 1 plus pi square over this. Zeta square. This whole thing will be 1 divided by this whole thing, right?
Right.
So you take if you add these two numbers, these two quantities, this ln square will be multiplied by 1, right? This whole thing will be by ln square, and that whole thing will go on the numerator. And if you take, since it is square, if you take just zeta, it will be this ln square, the whole square root, and you can take the square root off in the numerator.
So you're saying you just can't take the denominator of ln squared right there and bring it to the top and leave it 1 plus pi squared on the bottom?
Say it again.
You can't move ln squared, the pi, what's below pi squared right there. So can you not just bring that to the top?
No, you cannot.
How come?
Here it is like this, okay? It is A equal to
That's if it's attached to it.
B over 1 plus C over D, right? You cannot just bring D here. You have to make this B over D plus C over D, and then it can go here. Does that make sense?
Yeah.
Unless it is completely over, you cannot bring it up.
I mean, I thought if it wasn't attached that you could, but I see what you're saying.
Okay. So here, where does the negative come from?
The one?
Huh? You can say that. You can figure it out.
Where did negative come from? If it's not from that one, then I don't know. It's not that. It's not from the one, right? You.
Figure out where the negative came from.
Isn't it the one that was attached to the theta? Didn't that be when you brought it over? Is that negative now? It was positive before.
No, you divided by that. I thought. Let's see.
Yeah, that's
Y'all didn't want him to work this out. Y'all funny. Y'all knew this, huh?
He said you knew it.
It's easy algebra. That's what I said.
You know, I said it would take me some time. That's what I said.
Tony said, we don't need to show this out. This is easy.
Yeah.
This is
It
easy.
makes sense to me.
Oh.
You on your phone over there. Be quiet.
No, I'm not.
You're really on it right now?
You're going to testify in front of the colonel, okay? Everybody's going to testify.
Against me.
Honestly, Dr. Cindy, I don't know where you got the negative.
There's
Only thing I
a
can think
trend.
of is
I've noticed.
that
No,
negative
no,
in
no,
front of
why?
your E. What happened to that?
Hmm?
You see what I'm talking about? Your E,
That's what I'm saying.
the negative
It's a
that happened
bunch of-
in front of the parentheses.
Because it was
Yes,
one
yes,
line
you're
of
right,
space.
right.
What?
So when you do that, it gets
Against the.
Yeah, that's the only place I can see it.
What's up?
I don't like these accusations.
Yeah, that makes sense.
So you're saying because you have the negative in front of the small e, when you take the ln of it, then it goes to negative? That's what you're saying?
Remember, he had a factor.
See, here it is negative, right? So this remains negative. Okay. And you can say, if you bring it on the other side, both of them, no, still one of them will be positive. Figure out. I think you guys can figure it out. It's not that difficult. Anthony will figure it out, okay?
Oh, jeez.
I think you had.
Dr. Science will go back to his office and trying to figure it out.
Okay, don't worry, Doctor. Send me. I'll take a picture. I'll figure it out. I'll send the answer to you later today. Probably not, because I gotta go get my oil changed.